Hey guys, thanks for joining. My name's Kevin, and today I'll be talking about the kinematics and simulation work I did for my robotics course as part of the NASA Lunabotics rover that me and my team are developing. So a little background of the competition will start, then the specific project tasks relating to the robotics course, the mathematical model for the rover, the simulation of the rover, and then some integration testing, conclusions, and references. So what is the NASA Lunabotics competition? Well, it's a multi-university engineering competition where universities across the country compete in developing a regolith mining robot, or rover, and we have specific constraints from NASA, and at the end of next semester, we'll have a competition to see whose robot performs the best. And currently, I'm the EECS team lead, which means that I help orchestrate the electronics side of things in partnership with mechanical engineering department, who also contributes a lot to the development of this rover. In terms of the specific project in the robotics course side of things, the overall project has 5 different phases. So the first semester has phase 1 through 3, which is the scoping and problem definition, and the research and the best ways to optimize the system, and the hardware design. Then the second semester is 4 and 5, which is building, and then the debugging phase. And with this timeline, it means that the Robotics 428 course project is simulation only work. And this will allow testing of our software and our algorithms, even if the rover isn't fully integrated, which means we can start that early, which is great because software takes time to develop. Here's a quick image and review of the CAD model provided by the ME team, and kind of giving an overview of the actual rover that we're in the process of building. Now, although the 428 robotics course is entirely simulation based, that does not mean that hardware design work isn't being done. Here is a quick review of some schematics, some components that we have. We have our control loop for the motors, we have our power circuit, we have some calculations we need for the batteries, as well as the controller board, the NVIDIA Jetson, which is an embedded GPU and CPU unit, which is great, so we can do our computer vision processing for our path planning. It's a fairly complicated system, which is also why we're taking the full 2 semesters to build it, in line with the NASA competition timeline. So for the robotics course, we were tasked with kinematics modeling and then simulation. So the kinematics model of the true system has 4 wheels. It has the chassis and the camera. It has 3 degrees of freedom, so it has the translation in X, it has the rotation in Z, but it also has translation in Y, but not accessed directly. It has to translate in X and rotate in Y in order to achieve the motion in Y, so that's why it's called a non-holonomic system. And I tried to make the DH tables for the chassis to the wheel, and although I was able to derive those, since it was only one joint transform, it seemed a little bit like overkill, but I included the tables just for thoroughness. And so what I ended up doing instead was using a homogeneous transform, because that also meant that I could go from the world frame all the way to the wheel frame without the worrying of the Y component messing up the DH convention. But after doing some iterations between the mathematical modeling and the simulation work, it was realized that because we were running ROS for the robot, the specific Linux distributions needed to integrate that were not compatible on my powerful machine, just due to some hardware and hard drive configuration silliness. It's SATA with RAID enabled, which means that it just wouldn't load either in virtual machine or in dual boot the appropriate Linux system. So I had to simulate on a older machine that didn't have quite the same compute power and severely limited the ability to process the full model. So I ended up switching to a simplified model, which is the differential drive 2-wheeled mobile robot model. As you see, the current frame, the robot base frame, is now where the camera is, which actually makes a lot of sense because the camera is what will tell you how far away things are in the environment. It also made the modeling for the left and the right wheel simple because it's just a translation across that Y axis. And we have the overall transform matrix from the world frame to the base frame, and then to the wheel frame. Now, one problem with this in the real world is that because the two wheels on both sides of a four-wheeled robot, their arc is not the same when they turn, there would be slippage if they were driven at the same velocity. But because we're in a lunar regolith environment anyway, that doesn't really matter. It's not a big problem for our system, so that's what we'll do. We'll drive both right and both left at the same velocity, and if there's a little slippage, that's fine. So forward kinematics problem statement is find x and y, and of course the pose of theta given the parameters of the system, so wheel radius, the axle width, and then the history of motion between the wheels. But something to consider is that, let's say we have the wheel and it's, pi over 2 rotation. Well, how do we know it's not 8 pi over 2 rotation? How do we know that it hasn't already rotated a number of times before getting to that pose? And we can't, so the entire kinematics has to be done in the velocity space. And then if we want position after that, we can integrate it, and that's that. It just ends up being a lot easier to work in the velocity space. And so here are some of those kinematic equations, a little bit of simplification done. So on the right here, we have the position and velocity, sorry, not the position, the velocity based off of the wheel velocity. And we see that this can actually be simplified fairly nicely into just the linear velocity and then the angular velocity. Now, for the inverse kinematics, find the wheel velocities to achieve a given desired position. Well, there's infinitely many solutions to that problem. Essentially, the robot could just go straight forward, do a big bunch of spins, and then turn directly and get to that point. Or it could go directly to that point and then spin around a bunch of times to reach the desired pose. So it's an under-constrained problem. So for the mathematics, all that was done was take the inverse of the simplified forward kinematics model to get the inverse simplified model. Now, for the simulation work, as mentioned before, we have a ROS backbone, which is a middleware that essentially has graph or node-based architecture, and each process has its own node, which passes messages between them. And these messages could be as simple as a scalar, or it could be full readouts of information, such as velocity in linear and angular, as well as timestamps. So it's a really powerful tool in simplifying the kind of diverse nature of robotics development, where there can be many different processes running simultaneously. What's cool also is that it's kind of compiled or built with a language agnostic build process where you can program in Python or in C++, and it all compiles in the same compiler. So that's really nice. So if you have more experience in Python, you can do Python. If you have more experience in C++, you can do C++. Or if there's specific plugins or libraries that only work with one or the other, you can still use them and it'll still integrate very easily. So here on the screenshot, you can see some of the different aspects. We have the master node running in the terminal. We have another terminal that can show us which nodes we have running. So here we have some of the basic ones like ROS out, which is the master, as well as rviz and the joint states. So here you see from the blue on the left, it's a node that's getting the data from the joint states. It passes the message of what the joint states are to the robot state publisher, which will then eventually publish what state the robot's in. To get the simulation up and running, not a small task in terms of programming work. So the Unified Robot Description Format, .urdf, is the backbone, but involved in actually a full comprehensive simulation. There are a bunch of other files needed too, such as launch files to launch all of the models and all the different other files needed, the world files, which specifies the environment, configuration, the node files, which is essentially the source code, the build files, as well as there's some optional kind of better descriptive formats as well. You can see kind of some of the build tree on the left here, and most of it's done in XML, which, at least because most of the files are XML, it's kind of not too many new languages to learn, but because I didn't have as much XML background before, that was definitely a quick boot up. So to start from the code base to a simulation framework, RViz is a great tool. It allows us to visualize the links and joints of our robot, although it doesn't involve the physics. So it's not a true simulation environment, but it allows us to get the mathematics fleshed out so we can go directly after that, as well as it receives plugin and sensor data from the true simulation environment. So what that means is that if we're using LiDAR, for example, shown here, we can see that output from the sensor in the RViz visualization plugin or tool, whatever you want to call it, which brings us to the Gazebo part, which is the full physics engine enabled simulation, which has inertia, collision, gravity, all that. We have just the Gazebo only screenshot here, and then we have kind of a screenshot of what the entire system looks like, all running at the same time. So like I said, we have the LiDAR, we have the camera that's on the front, we have the ROS control terminal running, and then we have our simulation environment Gazebo running in the background. So with that, we'll jump to the video. So here's RViz. We can see, you can move the frame around in view, and those arrows pointing back are pointing back to the base frame. And at this point in the development, I was still using the four-wheeled configuration before I realized that running it through Gazebo was just going to take for absolutely ever. So we have a quick view of this booting up, and I ended up having to speed up this recording something like 15-20 times to have it play back in any reasonable amount of time, just because, as I said, the hardware that I was running the simulation on was incredibly lacking in compute power based off of what we needed. So because of that, there was actually some message passing issues as well. So what happened was that the latency was just so bad that it would drop messages. And so that's what's happening here, is the calculated time based off of what should actually be passed as messages to the rover, messages were being dropped. And so I actually had to average out the number of dropped messages so I could control it to a reasonable precision. And so that's why even though it should have been able to be precise, it wasn't actually able to be precise. It was only kind of based off of that average, and there was no real way to control the number of messages that were dropped. But you see here that it's performing as it should. It has the avoid obstacle node that I built, which takes the messages and then will navigate its path through the obstacles. And you see that it's printing the messages about it being close to stuff. So you see the LiDAR and you see the camera view up here changing as well. And then it will advance. Then it'll follow its same path back to approximately the origin. Again, as I said, from the dropping of the messages, it would only be generally precise and not fully precise, which is a little frustrating, but luckily we have a team member who has a more powerful system that actually was able to get the correct Linux and ROS distributions installed correctly, so we'll pass off the model to their computer, and for any future stuff, we'll be running it on their system. Hooray! Back to base. So the next steps are the integration phase, which again mentioned is going to be next semester from January to mid-February. That's going to be our hard time limit for that, because the competition, although in many years has been at the end of April, this year it's specifically early at the end of March. So that build phase will have to go a little quicker than normal. But again, we'll be able to incrementally add the software blocks that we need because of the simulation being ready. And it actually runs fairly similar to how it will run on a real robot, and allow us to develop the algorithms and then port it to the target hardware and do the little tuning that's needed, but it shouldn't be much more than tuning. And then the phase 5, that's the debugging and tuning phase, where we'll make sure everything works and is integrated to the target hardware. A couple conclusions. ROS is awesome. It's a really cool framework. It's very powerful for robotics, but it's a lot to learn. So that's the second conclusion, is that maybe for one semester project, don't take on 3 new software tools to learn, but maybe take on 1. But at the same time, this was going to be used for the next semester, so it made sense to at least start it. Then don't use a virtual machine if you can. The little 1 core that I had and the little bit of RAM that I had was very underpowered. And I just had the stat here, about 1 second was about 40 seconds in simulation time, so that's just not reasonable. Then the true simulation is incredibly complex, so moving from a 2D kinematic simulation to a 3D is big, but then also adding environment variables such as inertia, friction, that also really complicates the system and takes a significant amount more of compute power. And then lastly, the kinematics and dynamics equations were really helpful for debugging, kind of a logic-based check of the system, but so much these days is done in environments that have predefined variables, such as we had the twist geometric data type or message type in ROS, which already has the linear and angular velocity built in. So it's almost more like the simulation should be based off of that and then taken back to kinematics and adapted versus the other way around, because that is already a built service and having to rebuild that from scratch would have been a much more complex task. And then lastly, there was a bunch of new softwares and tools learned, such as ROS, the ROS Pi, ROS CPP libraries, the Gazebo environment, the RViz tool, Xarco, SDF, URDF, XML, CMake lists, VirtualBox, Docker. I tried to alleviate the virtual machine problem and got a little bit into it, but still more to learn there to actually get it running, and many more. We have our references. Definitely very helpful to have the internet and many other people doing these kind of developments. Couldn't have done it alone. And that's the end of the presentation. So hopefully you guys enjoyed it. If you do have any questions, you can post them in the comments. And other than that, till next time.